You mean today, is it?
Yes, Wednesday.
Oh, today, no. 12 o'clock. Since 12 o'clock, I have class.
Oh, okay.
Before 12, maybe I can consider.
Mm, okay.
All right. So, yeah, today we are at tutorial 8. So, we will be looking into the tutorial questions, and then we see how we can apply the knowledge of our lecture session here. So at least you will have a rough idea about how to, solve the real life situation in terms of problem solving. Okay, so I'll be recording the session. Any question you can ask me. Right. Can see the tutorial question, right?
Yes.
Can see the question screen.
Yes.
Okay, all right. So the first question, you are interested in the proportional control of a heat exchanger where the products from a reactor are to be cooled using cooling water. Okay, the transfer function GP relating the exchanger exit temperature to valve signal changes can be described by a first order transfer function with the static gain of 0.5 and time constant of uh, 5 minutes. So the 0.5 here is the K value and 5 minutes is the tau value. Okay. A disturbance to this system is the cooling water temperature TC. The transfer function GD, okay, GD is the transfer function for the disturbance relating temperature to TC, okay. Relating temperature to the cooling water temperature is first order with a gain of 1 and time constant of 6 minutes. Assume that the sensor is fast relative to the other components. Okay, so before we attempt the question, we better, how to say, extract all the information and put in a sketch first, so at least we can visualize what exactly they are talking about. Okay, and the first part of this question, they're asking us to draw a block diagram for this system, so we need to summarize everything in a block diagram. Okay, so before that, let's summarize whatever information given in the question. Okay, let's say we have a system here. All right, proportional controller system, proportional control heat exchanger they're talking about. So we have a hot water coming in, okay, and leaving the exchanger as cool. All right, and exit. Okay. So when it is exiting, it is cooled. They have mentioned that cooled using cooling water where the products from a reactor are to be cooled. Okay, they already mentioned that. So now, in this case, we also can summarize these things passing through the whatever the exit coming out from the exchanger is passing through a sensor, okay, or we call that transmitter. So here, when it comes to transmitter, we will have a transmitter temperature and the temperature of the um, inlet. Okay, so that is one thing, and then another thing, we will be having a temperature controller here. Okay, for cooling temperature, and it will be passing through a valve. Okay, All right. So this is basically a cooling water. Cooling water, and from this valve it will be going to the heat exchanger and the cycle goes on. Now they ask us to draw a block diagram for this system. All right, and it is already mentioned, it is just the proportional control. So P control controller, P controller. All right. So for a proportional control of heat exchanger, we can write the how to say we can write the transfer functions for the first order. Okay, for the first order in which the temperature and valve is related. Okay, so first order function, they have already given the k as the 0.5. If you remember the general function k over tau s plus 1, right? So the k is given as 0.1 and then tau in this case is 5 minutes. So 5s plus 1. This is for the temperature and valve portion. Now, when it comes to temperature and cooling temperature, or we can put that as TC. Okay, TC. We can express that using the same general transfer function formula, but for this case, they already mentioned gain as 1. So we're going to have 1 over and the time constant as 6 minutes. So 6s plus 1. Okay. Okay. This is for the cooling water temperature and also for the inlet temperature. Okay. So now we have another device here, transmitter. So when we want to how to say measure the ratio between the transmitter, okay, it's going to be T measured over the T actual. Okay. So here here it is equals to 1 because fast sensor. Okay. And the gain, meaning from this, we can conclude the gain or the K equals to 1. All right. So the time is the tau in this case. If you notice here, it's supposed to be tau s plus 1, right? So for us to get this, it's supposed to be 0. So here, the time constant will be 0. Or we call it infinity fast. Okay. This is still the information that we got from the question. Okay. Now the first question, they asked us to draw a block diagram. For us to draw a block diagram, we need to have a set point at the initial and how to say the measured or targeted value, measured or actual value of the system. So before that, for the set point, okay, it will pass through a controller, which is a proportional controller in this case. So will be how to say express that in terms of K, and we will be having a valve 0.5, 5s plus 1. So this is the transfer function for the T over V. All right. Okay. Now here the portion at which the outlet of the valve will be. So at this point, the information will be identified, and then the outlet will be the measured value. We call it as T. Okay. Now here we will be having a disturbance in which expressed as 1 over 6s plus 1. So this is the disturbance in this case, and it is a heat exchanger, so water is being recycled, or I can say it is a closed loop system. So it will be recycled from here to the initial point. So this is the diagram basically for the heat exchanger. system with the proportional controller only. Okay. Now, second part of the question, derive the closed loop transfer function TSP and T over TC. Okay, in terms of the controller gain KC. Okay, we need to express in terms of KC. So for us to do that, our first all right. All right. So for us to do that, first they're asking us to calculate the T over TSP, right? All right. The output over the input. Okay. So this can be expressed for us to get a output at the end, the T, it is actually the forward direction. And then here it will be the set point can be the inlet, okay, plus with the forward feedback. All right. So this will be for the set point value. Now for the forward portion, if you notice the diagram I draw just now, we have a Kc, okay, times with the valve transfer function, which is 0.5 times 5s plus 1. And for the input, we have 1 plus the forward is the above mentioned 0.5 5s plus 1, and the feedback will be the equals to 1, in which T measured over the T actual is. Okay, so with this, when we how to say summarize simplify this, we'll be getting 0.5 Kc. We can cancel these two, but let's leave it as this first. 1 plus 0.5 Kc over 5s plus 1. Okay, so this is for the T over SP. Now, secondly, we need to, you can actually further simplify this. Okay, when you further simplify this, you'll be getting 0.5 Kc over 5s plus 0.5 Kc plus 1. Okay, all right. This is the first part of first question. The part B. Okay. The second part of part B, they ask us to calculate the T over TC in terms of the controller gain also. So if you notice, the T over TC is actually at the disturbance portion, in which disturbance will be introduced here. And then the TC at the controller portion, so or the cooling portion will be having the 1 plus forward times feedback. Okay, so the disturbance transfer function, as we calculated just now or expressed just now, is 1 over 6s plus 1. And for the forward feedback, similar to what we did for the T over SP, it's 0.5 Kc, 5s plus 1 plus 1. Okay, so this is equals to 1 over 6s plus 1. Okay, simplify this, you'll be getting 5s plus 1 plus 0.5 Kc over 5s plus 1. Right. Can further simplify this as 5s plus 1 over 6s. So just remain that as it is, 6s plus 1, 5s plus 1 plus 0.5 Kc. All right. So this is for the T over TC. Now part C, draw a simplified diagram, block diagram of this control system showing the transfer function T over SP and T over T over TC. Okay, we can actually combine these two for the set point and the TC actually. So the simplified diagram will be done. Okay, so the simplified diagram will be T will be getting a input for the TC, which is already expressed for the transfer function form. Okay, see, this one already we expressed just now, right? So this is for the pulley, all right? So now we also going to have another input in terms of set point input, and this is already calculated for 0.5 kc over 5s plus 1 plus 0.5 kc. Now this will be the form in which both also will be inserted together. All right. So that is for part C. But then we also, how to say, we also need to explain, if can be able to explain the what we derive here will be better. So we have to make sure all the variable shown here in which the TTC in this condition, the TC and SP are deviation variables. Okay. So since they are in a diagram and transfer function, only use deviation variables. It can be deviated. Also, we can say that the TF, the transfer function actually rearranged in one more step so that the standard form of the equation we can get in terms of the gain and the gain and also the tau s plus 1, something in this portion. So the thing from here, initially they want us to calculate the T over TSP, and the second one will be the T over TC. So these two equation actually can be expressed in terms of this simplified. All right. All right. So part D, we need to determine the controller gain so that a change in set point results in offset of less than 10%. Basically, we need to calculate the KC, solve for the KC. And the set point results in offset of less than 10%. So okay. We actually, the set point change, they didn't mention the exact value, right? They only mention less than 10%. So for that, we actually can express the set point in a unit step. So for unit step, we can put the set point as 1 over s. Express this in the unit step. Remember this is the unit step expression for set point if set point is not specified. Okay, so we have a T over SP function earlier in which 0.5 kc over 5s plus 1 plus 0.5 kc. Okay, and from here we actually can express the T in terms of set point. So set point here, as we earlier already how to say express it. So we're just going to replace this. Okay, for us to find the offset, we need to find the final value theorem. Okay, final value theorem, as I mentioned in the lecture session, we need to find out the value for this function when the s approaches 0. So the limit of y function in which the t approaching infinity, we can equate it for the Laplace transfer function final theorem as approaching 0. So if you notice here, as approaching 0, this term will be cancelled out. Okay. This term will be cancelled out. So what we're going to do for final value theorem, we can express, for us to substitute the final value theorem, we need to calculate this first. So as okay, as y s, in this case s t s. All right, so we need to multiply with s first. S times with the ts here is the 1 over s, 0.5 kc over 5s plus 1 plus 0.5 kc. Now, this and this can be cancelled out. Okay. Now, the final value theorem, the s is approaching 0. So, this portion also will be cancelled out. So, for that, we will be having 0.5 kc divided with 1 plus 0.5 kc. All right. We need to find the kc value for offset less than 10%. So less than 10%, let's say reaches, the t reaches, if less than 10% offset. Okay. Let's say t reaches 0.9 or 90% of a unit step lah. T equals to 0.9, or we can say 90% of unit step. Okay, so with that information, we actually can calculate the QC. So when T equals to 0.9 equals to 0.5 kc over 0.5 kc plus 1. Okay, we can solve this and we'll be getting the kc equals to 18. Okay, so this is for part D. So that's how when they mention the offset is less than 10%, we basically can get the value of 0.9. Substitute for the T, in which express as the unit step expression. Okay. So part DE, they're asking us to determine the offset which results when a step change in TC of 5 degrees Celsius is implemented. So we need to calculate the offset when a step change in TC of 5 degrees Celsius is implemented. So this, what is the meaning of, what is the offset? First, we need to calculate what is the offset if step change Tc equals to 5 degree Celsius. So if you notice from the above, the earlier question, we obtained the Kc as 18, right? So we keep this, all right? So when the Tc expressed in terms of set point or Laplace form, we can say 5 over s. Why 5 over s? Or I can say this is a function of Tc and I want to express this in terms of set point. Okay, set point, unit step, sorry, unit step. So I can express this as 5 degrees Celsius. So this will become 5 over S. This is for TS. So for us to calculate the offset, we need to know the initial and final condition also. So that can be expressed as T over TC equals to the T here is the, okay, and TC is the 6S plus 1, 5S plus 1 plus 0.5 Kc. So T can be calculated by multiplying the TS. So it will be like 5 times 5S plus 1. Okay. This is one term over the S from the step unit step expression. So S 6S plus 1, 5S plus 1 minus, sorry, plus 0.5 Kc. Okay, for us to solve this, we know the final value theorem in which the limit of t in terms of t, in which t approaching infinity can be expressed as limit of s t s when s approaching 0. Now we already expressed this in terms of set point unit step change ready. So we will be how to say expressing or omitting the or simplifying these equations. So t equals to 5s times 5s plus 1 over s 6s plus 1, 5s plus 1 plus 0.5 Kc. So when the s equals to 0, so this s and this s can be cancelled. This one can be cancelled, cancel, and cancel. All right. So that will leave the equation as 5 5 times 5 times 0 plus 1. Okay. So this will be just the 6 times 0 plus 1. Okay. Here it will be 5 times 0 plus 1 plus 0.5 Kc. All right. So when we cancel out the 5 on top here, this portion, it will be just 5. Okay. Over, and this one will be just 1. All right. So here also 0 ready. It is just 1 plus 0.5 Kc. Right? So the Kc from the earlier equation question we already calculated as 18. When you substitute, you'll be getting a 0.5 degree Celsius of the deviation in temperature. Right? So that is to answer the offset. All right. But this is in units. So actually, for us to calculate offset, we can minus the desired value minus the actual value. Sorry. The desired value minus the actual value, right? Okay. Right. So the desired value in this case for a disturbance is equals to 0. Okay, and actual change we got from this question as 0.5. So having said that, the offset will be 0.5. If you want to rectify this answer, you can always calculate the percentage of disturbance magnitude and you will be getting the 10% as mentioned in the question earlier. Okay, so this is for question number 1. Vidam. All right. So second question, you have set up a PI control system. Earlier it was P control system. So now a PI control system to control the composition C of a stream leaving a reactor. Okay. The manipulated variable is the valve position on the valve, which supplies steam to the jacket of the reactor. In order to model the system, a step in the valve position of 10% was implemented and the composition of the product in the reactor effluent is shown in figure 1. Okay, the figure is shown here. Right. Now, if we sketch the positions of the PI control system that is described here, we know that we have a controller, okay? But we also know that the composition of a steam, not stream, steam, okay? So we have a PI control system in which valve is placed. Okay, we have inlet and leaving the system. So this is the steam. Okay, we have reactor at this portion. Okay. Okay, so the bottom portion coming out from the reactor is the effluent portion. We need to, the question asking us to composition of the product in the reactor effluent. So the composition here we don't know, we need to calculate. All right, and here we also will be having a controller which control the system or identify the malfunctions of this. So this one will be coming out from the effluent portion. Reading will be read by a controller and adjust the value that is going through here. All right. So this is a controller with 10% step change in value. The first question they're asking us to determine the parameters of FODT to control the composition C of a stream leaving a reactor. Okay, so parameters of FODT transfer function which could be used to model the system. So if you remember the FODT model, Okay. The step change that they mentioned earlier is the 10%, right? Okay. So this range is actually 0 to 100%, in between 0 to 100%. Also, meaning the step equals to 10 units. Okay. So we can express that as output at steady state over the input step size. Okay. So the output will be the from the 10% is 3 over the 10. Okay. So because for us to calculate the FODT, we need to calculate this first. So it will be 0.3. Now, all right. So we also can calculate, for us to calculate the FODT, sorry, for us to calculate the FODT, we need to find out what is the tau value. Okay, what is the tau value? For the tau calculation, we know that the 28% of 3 will be the 0.84, and the balance 63% to make it 100% of 3 will be the 1.89. Okay, so from here the T28 we can calculate from the graph. So T28 will be 11.5 second, and for the T63 it will be the 16.5 second. Okay, with these two values we actually can calculate the tau. Tau will be 1.5 times the T63 minus T28, and we'll be getting 7.5 second. Okay, I just put SEC because if I put S, you're going to confuse with the step unit step change. All right. So with that, we need to calculate the TD for the FODT. Okay. First, to calculate the TD, the T63 have to minus with the tau. Okay, and we will be getting 16.5 is the T63 minus the tau is 7. So that the TD will be 9 seconds. Okay, so with all this information, we can express the FODT. All right, so the step change is 0.3 times e to the power of the TD is 9 s over, and then the tau is in this condition is the 7.5 s plus 1. So this is the expression for FODT, right? Next, they ask us to calculate, draw a block diagram for this system. So with all the valve, the KC and the disturbance, the KC and the effluent input and everything, we need to summarize everything in the diagram. They ask us to calculate, just draw the block diagram. All right. So the first input of any block diagram will be the set point. All right. Okay. So we will be having a controller in which the P control. Okay. 1 plus 1 over tau 1s. And we will be having the FODT function also. And this will be the reactor effluent composition. And this is a recycling, how to say, close loop diagram. Okay, so we'll be having a transmitter or a reader measurement will be done, and then the changes will be do at the set point so that it will reach the targeted value. All right, so this will be the closed loop diagram. They mentioned the block diagram, so make sure you block everything lah. All right. Now, write the closed loop transfer function C over SP. So we need to calculate what is C over SP equals to. So again, for a C over SP, we need to know what is C first. Okay, C in this case, if you notice, all right, is in terms of the KC, and then in terms of the FODT. All right. And for the set point, it will be the 1 plus tau is the, 1 plus KC times with the PI controllers. So this is P, this is I, so we need to multiply. So C over SP equals to KC, 1 plus 1 over T1S, 0.3 E negative 9S, 7.5 S plus 1, 1 plus the PI is the KC, 1 plus 1 over T1S, okay, times with the PI controllers, FODT. Okay, this is actually, if you notice, this portion is for the forward section, and this will be the 1 plus forward times with the feedback. Okay, it's in that position. So this is the expression of the transfer function for closed loop. And of course, you can't leave it as it is. You need to simplify all the KC and T terms here. So when you simplify, you'll be getting 0.3 KC, 1 plus 1 over T1S, E negative 9S over 7.5S plus 1 plus KC, 1 plus 1 over T1S, E negative 9S times 0.3. So this is how we express the C over SP. Okay, it has to be in the form of forward over 1 plus feedback times the forward direction. Okay, so you need to simplify and then come out with the final step shown here. All right. The next part, determine the steady state offset, which results when a unit step change in set point occur. Okay, so we need to calculate the offset when a unit step change in SP occur. So what they mean by changes in SP occur, that means they have expressed the SP as 1 over S. All right. So when the changes in set point occur, we need to replace SP at all the expression as 1 over S. Now in final value theorem, the composition can be expressed equals to infinity when the function is expressed as limit of when the s approaching 0. All right. Now, so in this case, the composition equals to 1 over s, because set point is already taken to the right hand side, times with the s, we have 0.3 kc 1 plus s. So if when this is in the form of 1 over ts, when s approaching 0, this will be an issue for us to solve. Okay, so when s equals to 0, it will basically will give infinity. So we need to rearrange this form. Okay, we rearrange this form so that we don't have any leftover denominator in terms of s. When you rearrange, you'll be getting the c this and this can be cancelled out. So 0.3 kc P negative 9 0.3 kc e to the power of negative 9 s okay times with t1 s plus 1 t1 s. It's actually can be expressed in this form over simplify the bottom denominator portion in which 0.3 kc t1s plus 1 over t1s negative 9s. So this is not the last form still, can be simplified further. You'll be getting 0.3 kc because we still have the t1 over s at the top bottom here, right? So we need to omit that. So we can express this as simplified and okay. And this will give by cancelling the TS, the TS at this portion. We are not done yet. Okay. When you simplify, you'll be getting the s squared plus t1s plus 0.3 kc e negative 9s T1S plus 1. Okay, this will be 1 over the T1S. Okay, while you are rearranging the whole equation, you will be getting in this form. All right, when you get like this, sorry, here also T1. Okay, when you get like this, you can actually cancel the S and S term so that we don't have a denominator in terms of S. Okay, so now final value theorem, when the S approaching 0, we will be getting the CS as 0.3. So 0 means this one 0, this 0, this 0, and this 0. Okay, so that will give us KC E negative Y here 0 because here the 9S also 0. Okay. So we'll be getting 7.5 T1 times 0, so that is become 0 already. Okay, plus 0.3 KCE negative 0, 0 plus 1. Okay, this and this can be cancelled, right? Cancel, cancel, and cancel, and that will only leave with 1. So for 1 unit step change, here what they mean by this is 1 unit. Okay, 1 unit step change. C increases by 1 unit. So offset will be as set point minus the actual value or measured value over the set point. Okay, or this one to calculate the offset. Okay, so when the set point is 1 and the actual is 1 over 1, we'll be getting 0. Okay, so basically the function of PI controller, they eliminate the offset. The offset will be 0. So that's why they prefer PI controller over the P control system. Okay, in which the outcome of the process or the system will reach the set point that fixed earlier. All right. So that is part 2. Now part 3. A proportional only temperature controller. So here P only is used to maintain the temperature of a jacketed batch reactor by adjusting the flow rate of coolant to the jacket. The coolant valve has a gain of 1.5 liter per minute and a time constant of 0.2 minutes. Increasing the coolant flow rate by 1 liter per minute causes the reactor temperature to fall by 6.3 degrees Celsius after 10 minutes. And the temperature falls by a total of 10 degrees Celsius at steady state. The temperature transmitter probe is very fast and very accurate. So its dynamics can be omitted. So meaning when it comes to transmitter, we can actually omit their the behavior and their dynamics. Okay. So at part A, determine the transfer function for the valve, the proportional controller, and also for the transmitter, right? So whatever information given here, we just extract first. All right. So first we need to calculate the GB, right? So from the question, the KC or the gain of the coolant ball the Kc is or the Kv lah. In this case is given as 1.5 liter per minute, and the tau here or the time constant here is 0.2. So 0.2 s plus 1. So we have expressed for the Gv. All right. Later temperature falls at by 6.3 degrees Celsius after 10 minutes. Okay, meaning initially it was how much? It was, is they mention how much it initially was? Falls by a total of 10 degrees Celsius steady state. Okay, total of 10 degrees Celsius, meaning okay, first the reactor T falls at 6.3 degrees Celsius after 10 minutes. All right, and falls to 10 degree at steady state. Okay, so from here we can calculate the gain of the proportional controller as -10 since the temperature fall. Okay, and the tau p after 10 minutes, right? So 10 minutes. This is for the tau proportional controller. So the GP or the transfer function of proportional controller can be expressed as tau k here is the -10 over the tau is 10 plus 1. Okay, so GV is expressed, GP is expressed. All right. They asked us to determine the transfer function of GM, and if you notice in the question statement, they already mentioned the dynamics can be omitted. Okay. Now, draw the closed loop block diagram for this control system. So we know we have like a valve, P controller, and then we have the how to say KC portion and also the transmitter, right? So we can draw this actually very easily compared to the previous section, right? Let's draw for the standard proportional controller system. Okay, we will have a set point. All right. So let's see, they set the temperature at this portion ready, and then we'll have a KC, move to the valve, valve transfer function, and then to GP, and we have our output. Okay, it's a closed loop. So we will be recycling or circulating the, sorry, it's supposed to goes in at this portion. Okay, usually that's how we draw the block diagram. And if you notice here, the transmitter will play the role. Okay, the position of the transmitter. Okay, derive the closed loop transfer function for a set point change T over T set. All right. Now, for a set point change T over T set, in order for us to derive the transfer function for that, first we need to start with the T over T set is given in the question. So for the T outlet, the output here, if you notice, it is actually the multiplication of Kc times Gv and Gp. All right. And T set is the 1 over Kc, Gv, and Gp. Right? So here the Kc, the Gv is calculated earlier, or how to say, expressed earlier as Gv is 1.5 over 0.2 S. So 1.5, 0.2 plus 1, and the Gp is negative 10 over 10S plus 1. Over the 1 plus Kc, the Gv given is 1.5, 0.2 second plus 1, negative 10, 10S plus 1. All right. Now, simplify all these. You can actually express the entire equation as negative 15 Kc.
This soup is 50 years old
0.2
and everybody's eating it. This is the Watanapanish soup
plus
from
1,
Bangkok in Thailand. It was started
10S
in the
plus
70s
1,
in this pan, and
Alright.
people are coming from all over the world
minus
to get a taste
15
of it.
Broth was absolutely
Kc.
amazing, and the beef was so tender.
All right. So, um, this portion actually can be expanded so that we know where to use the how to say, simplify more this portion. Okay, so negative 15 Kc over 2 S square plus 0.2 S plus 10 S plus 1. This is one thing, minus 15 Kc. Okay, so this again can be 15 Kc over, so we can bring out the or break the bracket here. This is actually 10.2 S plus 1 minus 15 Kc. All right. So the 15 Kc, if we want to simplify further, we can leave it as it is, or you can now simplify at this portion also. All right. So I prefer to leave it as it is, so that if we want to find the final value theorem, we can easily cancel out the when s approaching 0. All right. So yeah, that's all for today. Only 3 questions to solve. All right. Any question? Okay, so no question. I think we'll end the session. Thank you so much for your time, and see you all next week for the lecture session.